Hello guys, welcome back to this channel. Today's topic will be flow curve. We'll see how to plot flow curve for fine grained soils, and we'll see the 𝐷𝐷𝐷 limits. 𝐷𝐷𝐷 limits are important in fine grained soils. So the 𝐷𝐷𝐷 limits include the liquid limits, plastic limit, and sometimes shrinkage limits. We will see an index called the plasticity index. So if you are new to this channel, please subscribe to my channel and join for free, and stick to the end of this video to get free Excel template. You can use this free Excel template to plot flow curve for soils. So as you remember from your previous courses, the property of fine grained soils is dependent on mineralogy but also on moisture content. So fine grained soils properties radically change in the presence of moisture content. So we can calculate these changes and see how these changes affect the soils using 𝐷𝐷𝐷 limits. And to calculate the 𝐷𝐷𝐷 limits, we have to conduct some type of test. So one of the tests was using Casa Grande's apparatus to determine the liquid limits of a soil. Liquid limit is nothing but the water content corresponding to 25 number of blows. And to calculate the plastic limit of a soil, you have to roll a sample of soils until it shows cracks, usually at 3 mm in diameter. And plasticity index is the range of water content in which the soil behaves as a plastic. So let's see with this practical example. So a test was conducted on a clay soil using Casa Grande's apparatus. We are required to determine the liquid limit of the clay and determine the plasticity index and calculate the liquidity index of the soil. And from this investigation, we have the natural water content of the soil and the plastic limit. Notice as the water content is reduced from 52.5 to 37, we are required to do more number of blows. So the number of blows increases with a reduction in water content. So this plot shows the relation, the volume water content relation of fine grained soils in different phases. You have liquid phase, you have plastic phase, you have semi-solid and solid phase. Suppose you have a soil mass with excess amounts of water. So in such a case, the material behaves as a liquid. So if we reduce the moisture content by either adding a soil mass or by drying, it will eventually reach a point in which the soil mass, the liquid, stops behaving as a liquid and starts behaving as a plastic. And this point is called as liquid limits. It starts behaving as a plastic material. If we further reduce the water content by either adding soil mass or by drying, we will reach another point called the plastic limit, in which the soil stops behaving as a plastic and starts behaving as a semi-solid. And further reduction in moisture content will lead to a state in which this material will be rock solid, and it will stop behaving as a semi-solid and starts behaving as a solid, and that point is known as shrinkage limit. This shrinkage, plastic and liquid limit collectively are known as 𝐷𝐷𝐷 limits. You can see that from the plot. With an increase in moisture content, there is a reduction in strength. So soil material have larger strength in semi-solid and solid state, and they have low strength especially in liquid state. So we can numerically interpret this concept using liquidity index. So liquidity index value becomes less than 0 then the soil will be in semi-solid state and it will have high strength, so it will somehow behave as a brittle material. If the liquidity index is between 0 and 1, then the soil mass is behaving as a plastic and it is in a plastic state. It will have intermediate strength and it deforms like a plastic. And if the liquidity index is greater than 0, then it is in liquid state. It will have low strength and it flows like a liquid. So we want the material to behave as high strength material. So the liquid index as much as possible should be as either in less than 0 or between 0 and 1. So liquid limit is defined as the water content corresponding to 25 number of blows. So you can see this is a flow chart. On log X scale we have, so on the abscissa scale or on x-axis we have number of blows, on the y-axis we have water content. So the liquid limit is the number of blows corresponding to the water content corresponding to 25 blows. So in previous example we have a liquid limit of 40, but how does this 40 determine? So let's see that. So let's see how to construct flow curve for this particular question. So we have prepared a sample Excel template. We have number of blows on x-axis and we have water content on the y-axis. So let's copy the values. So we have the number of blows and we have water content. So this is how you plot the flow curve. So we want the water content to be, the liquid limit is the water content corresponding to 25 number of blows. So the water content corresponding to 20 blows is 43.2. The water content corresponding to 28 blows is 38.6. So by linear interpolation, the water content or the liquid limit corresponding to 25 number of blows will be 40. So subscribe to this channel to get this flow curve template. Let's just get back to calculating plasticity index. So the next, I'll estimate the plasticity index and liquid index. So the plasticity index is the range of water content in which the soil behaves as a plastic material. So plasticity index is the difference between liquid limit minus plastic limit. So the liquid limit is 40 minus the plastic limit 23. So the plasticity index is 70. And the liquidity index will be the ratio of the natural water content minus plastic limit divided by the plasticity index. So the natural water content is 38 minus 23 divided by 17. So the result will be 0.88. Since this liquidity index is 0.88 or between 0 and 1, it indicates that the soil, the material soil, is in the plastic state. So this is how you determine the liquidity index, plasticity index, and the liquid limit. If you find this video helpful, please don't forget to subscribe to our channel. Also subscribe to get the Excel template. I'll see you in the next video.